video, I'd like to talk about covalent bonding and molecular compounds as described in Chapter 6.2 of your textbook. Quick review. What is covalent bonding? It is the sharing of pairs of valence electrons between atoms. And now let's define some other terms. A molecule, a word I'm sure you've heard before, is a neutral group of atoms held together by covalent bonds. A molecular compound is a compound whose simplest unit is a molecule. A chemical formula is a representation of the composition of a compound that specifies which elements make it up and the relative amounts of each, expressed as the simplest integer ratio. So for example, we learned that with ionic compounds, the formula of an ionic compound is simply the simplest integer ratio of cation to anion in the crystal lattice. So for example, if I write the chemical formula of the compound made of magnesium and bromine, I'll write it as MgBr2, which tells me that in the crystal lattice of this ionic compound, there are 2 bromine anions for every magnesium cation. On the other hand, a molecular formula is more specific. A molecular formula is a representation of the composition of a molecular compound that specifies exactly how many atoms of each element are in a single molecule of that molecular compound. So for example, if I take the molecular compound glucose, which is blood sugar, that has the molecular formula C6H12O6, meaning that in every molecule of glucose there are exactly 6 carbon atoms, 12 hydrogen atoms, and 6 oxygen atoms, okay? 24 atoms in that molecule. Now notice that is not the simplest integer ratio of carbon to hydrogen to oxygen. So a molecular formula, which applies to a molecular compound, gives you more specific information. And here's a term I'll use later on, diatomic molecule. As the name implies, a diatomic molecule is simply a molecule made up of 2 atoms that are covalently bonded together. So, how are covalent bonds formed? Here I show you on the left a representation of 2 non-bonded hydrogen atoms. The positive charge in the center represents the proton in the nucleus, the circle represents the 1s orbital in the ground state, and the negative sign represents the electron. In the separate atoms, each electron feels the electrostatic attraction of its own nucleus. But as I bring the hydrogen atoms closer together, the 1s orbitals overlap and the 2 nuclei share a pair of electrons between them. Notice now that each negatively charged electron feels the electrostatic attraction of both nuclei simultaneously. Bringing oppositely charged particles together lowers the potential energy. This is how you form a covalent bond. And again, remember, chemical bonding is defined as the mutual electrostatic attraction between the nuclei and electrons of different atoms, which lowers the potential energy of the system. Let's look at a graph on the next slide that shows how the potential energy in the hydrogen molecule depends upon the distance between the 2 nuclei. So, here's a rather detailed graph. Let's explain what's going on here. On the x-axis is R, which is the distance between the 2 hydrogen nuclei. On the y-axis is potential energy. Far to the right, that is at large value of R, the nuclei are very, very far apart from each other, and therefore they do not interact. We will define that as a potential energy of 0. As R decreases, in other words, as the 2 nuclei get closer and closer together, as you can see, attractive forces predominate, the nuclei come together, the potential energy lowers, and ultimately we reach a potential energy minimum, the bottom of the well, which is the most stable state. As we bring them closer together, you can see now repulsive forces start to take over. The nuclei repel each other, the electrons repel each other, and the potential energy begins to decrease. You will see 2 very important numbers there. On the x-axis, the distance scale, 74 picometers, and on the y-axis, the potential energy scale, negative 436 kilojoules per mole. What are the significances of those numbers? 436 kilojoules per mole is defined as the bond energy, and 74 picometers is defined as the bond length, sometimes called the bond distance. So let's talk about what those refer to. The bond length is defined as the distance between the 2 nuclei at minimum potential energy. And we saw for the hydrogen molecule that corresponds to 74 picometers. That is where the potential energy of the system is the lowest. The bond energy is defined as 2 equivalent things: the energy released when the bond is formed in kilojoules per mole, or correspondingly in the opposite direction, the energy required to break the bond, also in kilojoules of energy per mole of bond. So if I look back at the diagram, I can see that going from large distance to the potential energy minimum, I release 436 kilojoules per mole of energy. That's why it's shown as a negative on the graph. But if I wanted to go in the opposite direction and break 1 mole of HH bonds, that is, separate them to a very large value of R, I would have to put in 436 kilojoules per mole. By convention, bond energies are listed as positive quantities. Somebody just decided that. And here are some examples of bond lengths and energies. So let's look at the halogens. Each of the halogens as a pure element forms a diatomic molecule: chlorine-chlorine, bromine-bromine, iodine-iodine. For chlorine-chlorine, the bond length is 199 picometers. The bond energy is 243 kilojoules per mole. For bromine-bromine, 228 picometers, 193 kilojoules per mole. And for iodine-iodine, 267 picometers and 151 kilojoules per mole. Pause the video and see what trends you observe. So we clearly see that when we are comparing similar covalent bonds, and these are similar because they were all bonds between halogens, as the bond length increases, the bond energy decreases. They are roughly inversely proportional. So why would the bond lengths in these halogen molecules increase as you go down the group, going from chlorine to bromine to iodine? Well, we learned earlier that as you move down a group, the valence electrons, which in this case are the ones being shared, are in higher principal energy levels, which contain larger orbitals. Therefore, the valence electrons that are being shared to form the bond are further from the nucleus, and that puts the bonded atoms further apart. So why would bond energy decrease as the bond length increases? Well, as the atoms move further and further apart, less energy is needed to completely separate them, which is what we call the bond energy. So again, as the bond length increases, the bond energy decreases. So this all leads to the question, why do molecular compounds form the formulas they do? It is observed that molecular compounds tend to form specific formulas. So for example, elemental hydrogen is only ever H2. It never occurs as single hydrogen atoms under normal conditions, nor does it occur as H3 or H4. Likewise, fluorine, like all the halogens, occur as diatomic molecules. Well, let's look at electron configurations. Here I can represent two hydrogen atoms by showing a horizontal line to represent the 1s orbital and one electron in each 1s orbital. When the hydrogen atoms are separate, each hydrogen only has one electron in its valence shell. But if the hydrogen atoms overlap their valence orbitals and share the valence electrons, each hydrogen atom now feels as though it's surrounded by two electrons, which is the electron configuration of the next noble gas, which is helium, 1s2. So by sharing a pair of valence electrons, each hydrogen feels as though its valence shell is completely filled, and it has the configuration of helium. What about fluorine? Here are two fluorine atoms. The valence electron configuration is 2s2, 2p5. Neither fluorine atom separately has a filled valence shell, but by overlapping two of the 2p orbitals and sharing a pair of electrons, now each fluorine atom completes its valence shell. It now feels as though it is surrounded by 8 electrons. It achieves what is called an octet of electrons, a term you may have heard of before. And that leads to a very important concept in all of chemical bonding, which is the octet rule. And the octet rule says stable chemical compounds form such that each atom, by gaining, losing, or sharing electrons, has an octet of electrons in its highest occupied energy level. Having 8 electrons corresponds to a special stability. So what is so special about an octet? Well, I hope this is clear to you. 8 electrons in the valence shell corresponds to a completely filled valence shell, which of course is a noble gas configuration, corresponding to NS2 NP6. So what can we do with this? We can do a lot. We can understand and predict molecular formulas. And now we are going to understand and represent molecular formulas by using what's sometimes called electron dot notation to draw what are called Lewis structures. They're sometimes called electron dot structures or Lewis dot structures. I just call them Lewis structures. The nuclei and core electrons are shown as element symbols. Shared electrons are shown as lines between the atoms, and unshared electrons are shown as dot pairs around the element symbol. Okay? And let's take some examples. In the hydrogen molecule, I have a total of 2 valence electrons. So I will show my hydrogen atoms sharing a pair of valence electrons, or preferentially, I will show the shared pair of electrons as a line. I think the line is a little bit neater than the two dots, but it means the same thing. The line represents a shared pair of electrons. In the water molecule, each hydrogen has 1 valence electron, oxygen has 6 for a total of 8 valence electrons. I can show the two OH bonds as shared pairs of electrons. I have 2 more valence electrons. They are placed on the oxygen atom as lone or unshared pairs to satisfy oxygen's octet, or preferentially using lines. I will show the 2 OH covalent bonds as lines, each of which represents a shared pair of electrons. The oxygen atom then has 2 unshared electrons. Notice that the oxygen atom is surrounded by 8 electrons, 4 shared electrons and 4 unshared electrons for an octet. Each hydrogen, by sharing a pair of electrons with oxygen, is surrounded by 2 electrons, which, again, for hydrogen, corresponds to a filled valence shell. Let's do one more example. Methane CH4, the main component of natural gas. Carbon has 4 valence electrons. Each of the hydrogen atom has 4. That's a total of 8 valence electrons. I can show each of the 4 CH bonds as a shared pair of electrons. There's my 8 valence electrons. Or, preferentially, I can show the 4 CH bonds as lines. The carbon atom is sharing 8 electrons. That is 4 shared pairs of electrons for a total of 8. Its octet is satisfied. Each hydrogen atom is sharing a pair of electrons. It is surrounded by 2. Now, in the next series of videos, I'm going to show you in great detail rules for writing Lewis structures and lots of examples. See you then.